Right, good. So you've had one lecture on multiplicity, and I've showed you how we can arise or get doublets and triplets and quartets, etc., etc. What I'm going to do now is show you how to sketch some spectra. All right, so the spectra that you are going to sketch, so these are the, can you see my screen? All right, so this is the spectra that we're going to sketch. And generally, if I have a molecule,
Prof.
yep.
Professor, I can't see your screen.
Okay, 1 second. Can you see now?
Yeah, we're good.
Perfect. All right, so generally we'll get some molecules like this where we're going to be required now to sketch some spectra. It's very important to be able to sketch some spectra, because if you make, just say you made one of these molecules and you want to know whether or not you made it, when you get the spectrum from the NMR, you must be able to very quickly see, am I getting what I'm expecting to get? Right? So we're going to analyze each of these molecules and see what is it that we are expecting to get, so that when we do get our spectrum, we can say, oh yes, this is behaving exactly like what I think it should behave. So let's take the first one, right? I've got a CH3 next to a CH2. So I'm going to look at this particular signal here. And if I look at this particular signal, it's next to a CH2. And that should give me a triplet. If I look at this particular CH2 signal, it's next to a CH3 group, and this should give me a quartet. All right, and the same thing here. The CH3 is next to a CH2, I should get a triplet. This CH2 is next to a CH3, I should get a quartet. So I'm expecting in this particular structure to see 4 different signals. And I'm seeing 4 different signals because I have this extra oxygen atom here that makes this molecule not to be symmetrical. If I didn't have this oxygen in here, then the molecule will be symmetrical and I'll only see 2 signals, right? But because the molecule is not symmetrical anymore, because I now have an ester with this oxygen in, I find that I have 4 signals. 2 of them are triplets and 2 of them are quartets, right? 2 are triplets and 2 are quartets. So if I look at the 2 triplets and the 2 quartets, the next thing I'm going to look at is where in the spectrum between 0 and 10 are these signals. So I'm going to say now that each of these resonances, are they going to be shielded or deshielded? And which is going to be more shielded and deshielded? So if I look at these particular resonances here, this CH2, that's a quartet. This hydrogen is bonded to this carbon that's directly bonded to the oxygen. So this is going to be the most deshielded. All right, that's going to be the most deshielded that you find here. This CH2 group, it's next to this carbon atom with the oxygen that's 3 bonds away, right? So that hydrogen next to a carbon, next to another carbon, next to an oxygen. So we find 1, 2, 3 bonds away, I have an oxygen. Here I have the oxygen 2 bonds away. So this is also going to be deshielded, but not as deshielded as this particular one, right? So I'm going to label this now, and I'm going to call this A and B and C and D. All right, and I'm going to sketch the spectrum of this particular molecule. All right, so I'm just going to sketch it down here, right, so that you can see it down here. If I sketch this, right, I'll call that 0, and I'll go 1, 2, 3, 4, right, and then it's 5, 6, 7 after that. All right, now if I look at the CH3 group and the CH3 group here, both of them are triplets, right? And I'm going to expect a normal CH3 to be around 1. But this, around this CH3 group, 2 bonds away, there's a carbonyl group. And here there's an oxygen about 2 or 3 bonds away here, all right? So if I look at these 2 CH3 groups, I can say that B is going to be more deshielded than D, because here I have a direct oxygen, but here I have a carbonyl group that's 2 bonds away or 3 bonds away, right? So 3 bonds away to this hydrogen, I have oxygen, and here 4 bonds away to this hydrogen, I have a oxygen. You can count the bonds later in your own time and you can see that's true. So with regard to B and D, B is going to be more D-shielded, right, than D. Both are going to be triplets, right? But B is going to be more D-shielded than D because the oxygen is closer to this proton than it is to that proton, right? Likewise, A and C. If there's an oxygen directly bonded to a carbon that's bonded to a proton, I'm expecting the CH2 group of A to be D-shielded somewhere around 4, right? So that's my quartet of A, right? I'm expecting it around 4, the chemical shift, because the hydrogen has an oxygen 2 bonds away. The C has the hydrogen bonded to the oxygen 3 bonds away. Hydrogen, carbon, carbon, oxygen. That's 3 bonds away. So it's not going to be as D-shielded as 4. It occurs somewhere around 2.1, 2.2 here. And that's going to be my C. Right, so that's the spectrum I'm expecting for this particular molecule, right? I'm expecting a spectrum like this, where I have A, which is the most D-shielded, followed by C, the second most D-shielded, then B and D are shielded, but the most shielded is going to be D, which is this particular one here. All right, so that's sketching the spectrum of that. And this spectrum is quite easy to sketch. This is going to be a triplet, right? I'm just going to say T for triplet because it's next to a CH2. This CH2 is going to be a quartet, right? I don't need to sketch the spectrum of this. I showed you something similar in the previous lecture, but if I had to sketch the spectrum, it's going to be very, very simple here, right? 0, 1, 2, 3. Just going to extend it a little bit more here. Around 3.5, you can see this proton is 2 bonds away from this chlorine. So around 3.5, you'll probably expect the proton group, which is the CH2, and that's a quartet. This triplet is next to an electronegative atom, but it's not 2 bonds away now, it's 3 bonds away, right? So 1, 2, 3 bonds away. So I'll find this triplet maybe on the other side of 1 that you find here. All right, so just 2 signals here, one for the CH3 and one for the CH2. Let's look at this particular one. Here, I have one group here, a CH group, and I have a CH3 group and a CH3 group. And now I can actually look for symmetry, and I can find symmetry in this molecule because I can see down this center here, I can have some symmetry, which means that this CH3 group is equivalent to that CH3 group. So I'm going to see one resonance for both of these CH3 groups, right? And one resonance for the CH group. And that's going to be in the ratio of 1:6, right? So that's 1:6. If I look at the multiplicities, this proton is next to 3 + 3, 6 protons. The n+1 rule, 6 + 1 = 7. So this proton is going to be a septet. If I look at these methyl groups, remember that these methyl groups are now equivalent, right? So both these methyl groups are next to a CH groups, and this is going to be a doublet, right? So this is going to be a doublet. So I find that I have 2 resonances in this particular spectrum as well. Right, not 1, 2, 3, and 4. All right. I have a proton that's next to a carbon, that's next to a bromine, and that's 2 bonds away. So this is going to be somewhere around 3 to 4, right? And that's a septet, right? So I can expect 7, 2, 3, 4, 5, 6, 7 peaks here, right? That's my septet. And you can see the septate is de-shielded because of the electronegative bromine atom. And then a doublet, I'm expecting somewhere here, around 1. I'm expecting the doublet there because it's next to just one CH group, right? This here is just one CH group, right? And if you look at this bromine, it's 1, 2, 3 bonds away from that hydrogen, right? 3 bonds away from that hydrogen, so it's going to be very shielded, not as de-shielded as something 2 bonds away from the bromine. And then the integrals here is going to be 6:1. Right, so the integration here is going to be important. This is going to be 6:1 because you can see they have 2 equivalent methyl groups on this particular molecule. All right, let's go to this particular one. Now I have 1, 2, 3, 4 proton groups, right? And the 4 proton groups that I have, this CH3 group is different from that, and that. But that, and that, these 3 CH2 groups are all equivalent, right? I don't know if you can see the symmetry here, right? Remember that around the central carbon, you have a tetrahedral shape, right? So that CH2 group, that CH2 group, and that CH2 group are all equivalent, and this is different. So I'll just get 2 resonances in this particular molecule, all right? I'm not going to, see many resonances. I'll just get 2 resonances. And the ratio is going to be 3:6 or 1:2, right? Because 3 protons here and 6 protons here. So 3:6 or 1:2. And let's look at the multiplicity for each of these. There's the proton on the carbon, and I look at my adjacent carbon. My adjacent carbon doesn't have any protons on it. It's just got carbons on it. So this protonated group here doesn't have any neighbors, n equals to 0. If n equals to 0, I'll just see a singlet. 0 plus 1 is 1. So I'm not going to see any multiplicity here. I'll just see a singlet for that, right? Likewise, these CH2s here. If I look at this proton and this carbon, and I look at the adjacent carbon that I see here, there's no protons on this adjacent carbon. I've got a carbon, and a carbon, right? So there's no protons next to this carbon. So I'll also see a singlet here, right? So you're ending up now with a spectrum, right? Not 1, 2, 3, 4. A spectrum where you just see 2 singlets. One singlet is going to be shielded, probably the CH3 here. All right, so I'll call this A and I'll call this B. That will be B, that will be B, because they're all equivalent, right? This A is not next to an electronegative atom, right? That's 2 bonds away to that carbon, and then 3 bonds away. So I've got a hydrogen to a carbon, that's 1 bond, to another carbon, 2 bonds, to another carbon, 3 bonds, to another carbon, to bromine, which is 4 bonds away. So it's not too de-shielded, right? And this is going to be my A resonance. But this CH2 group here is directly bonded to the carbon where the bromine is on, right? So these hydrogens here are bonded to a carbon where the bromine is on. So that singlet is going to be between 3 and 4, and that singlet is going to be B. And the integration here, as I said, is going to be 2:1 or 6:3. All right, let's look at E, this particular molecule here. And I look at the multiplicity. I've got a protonated group that's not next to any carbon with hydrogens on it. This is going to be a singlet. Then I got this CH2 group here that's next to another CH2 group. So this CH2 group is next to something with 2 protons. 2 plus 1 is 3. This must be a triplet. And likewise, the CH3 group is next to the same CH2. So because the CH3 is next to a carbon with 2 protons, this is also a triplet. All right, now, very importantly, all right, the splitting pattern or the multiplicity is only given by equivalent protons, right? So if I look at this particular molecule that I have here, these 2 protons and these 3 protons are not equivalent. So I can't apply the n+1 rule, even though I have neighbors on my left side and neighbors on my right side. Right? I can't apply the n+1 rule and see that I have 5 protons, 5 plus 1 is 6. Right? I can't do that. This is just going to be, well, in effect, it's going to be a triplet of quartets, right? Which is 12 lines. Right, but we're not going to go so much into detail with that splitting pattern and that multiplicity, right? So generally, if I have 2 proton groups next to it, right, I'm going to get a multiplet here. As I said, you know, the CH2 group is first split into a quartet, and each of those quartet lines is split into a triplet, which gives us 12 lines. And we're just going to see a big multiplet for that. We're not going to see the 12 lines because, you know, you can see how difficult it gets when you have 7 lines or you know, in the signal, imagine 12 lines. So we're just going to get a whole lot of overlapping there, and we're not going to see that properly. So we just call it a multiplet, right? So very importantly, you can't say that this CH2 group is going to be a sestet because there's 5 protons around it, right? It doesn't work that way. The protons have to be equivalent. All right, so let's sketch the spectrum and see how we're going to sketch it. I've got 0, 1, 2, 3, 4. And I'll start with my most d-shielded resonance. The most d-shielded one is the hydrogen bonded to a carbon bonded to an oxygen. So the electronegative atom is 2 bonds away. And that singlet, I will probably find somewhere around here, right, between 3 and 4. Right, if you're wondering how I'm just getting these values between 3 and 4, between 1 and 2, I discussed the table with you when I discussed the electronegativities and shielding and de-shielding, right? So you'll get some idea when you look at your tables in your textbook, right? You'll see where those values are, right? But generally, electronegative atoms like oxygen, chlorine, bromine, you know, shift the signal to somewhere between 3 and 4. So I'll accept anything between 3 and 4 is fine, all right? Then I've got two triplets here, a triplet here for the CH2 and a triplet here for the CH3. And the triplet for the CH2 is going to be slightly more d-shielded than the other triplet because of this carbonyl. And whenever you have a proton group that's next to a carbonyl group, then we have the signal lying just on the other side of 2, right? So this triplet I'm going to find here. But I'll label this here A, B, C, and D. So that's your A signal. This will be your B signal. And this triplet is de-shielded because of the carbonyl group. Otherwise, they'd appear around 1 or so, right? So that's where we probably find the other triplet, right? D, around 1 or so. And C, we probably find between D and B. And that's just a multiplet, right, that you find here. And that can be your C proton. Right, so that's the spectrum sketch for this. You can put in the integration if you want. 3:2:2:3. Right, so your D is going to be 3:2, and the B is going to be 2, and the A is going to be 3. Right, so that's your integration. 3:2:2:3. And the last example that we're going to draw the spectrum for is this particular example. And here again, the CH3 group is next to a carbonyl group and not next to any other proton. So this is going to be a singlet. This CH3 group is next to the CH group that we find here. So this is going to be a doublet, right? And this CH group is next to the CH3 group. So this is going to be the quartet. Right, so the neighbor, 3 protons, 3 plus 1 is 4, 1 plus 1 is 2. That's why a doublet and a quartet and a singlet here. All right, so if I sketch the spectrum for here, I'm looking at the most de-shielded peak first, and that's this proton that's bonded to the chlorine, and that's a quartet. Right, so the proton bonded to a chlorine, the quartet is around 3 to 4. So I have a quartet around 3 to 4. I have a doublet right? It's not as shielded as 1. It's probably on the other side of 1 because I have a chlorine, but that's 3 bonds away. So I'm probably going to find a doublet here. I'll put this as A, B, and C. So A, B, and C. And you can see that the C resonance is here and the B resonance is here. And I have another singlet resonance next to a carbonyl group, so around the 2 range. And this is going to be just a singlet peak that you're seeing here. And that's going to be due to A. You can put your integration in. That's going to be 3 is to 1 for the B proton. All right, so generally you can take any of your molecules that you see, right? And once you know about chemical shift and the atoms that affect the chemical shift, and here I've used a bromine atom as an electronegative atom. I've also used a chlorine atom and an oxygen atom as electronegative atoms to show you that those atoms will de-shield the protons on a carbon. They will take electron density from them and shift the signal. And you saw that in every case where you had an electronegative atom 2 bonds away from the proton, the resonances were shifted to about 3 to 4. If I had the electronegative atom that's 3 bonds away from the proton, the resonance was shifted to around 2 point something, right? On the other side of 2, right? Between 2 and 2.5 or so, right? So that's the effect of having an electronegative atom 2 bonds away and 3 bonds away, right? And if there's no electronegative atom 2 or 3 bonds away, then we see the resonance shielded close to 1 in your NMR spectrum. Right, and you can look at the neighboring protons in each of these molecules. And once you look at the neighboring protons in each of these molecules, you'll be able to then determine the multiplicity, whether it's a doublet, a triplet, a singlet, etc., etc. All right, I'm going to stop there for a few minutes to take any questions, and then I'm going to continue looking at some spectra. All right, so our NMR spectrum is on the base, NMR spectrometer is on the basement of chemistry, and you'll find there that we have, 2 NMR spectrometers of 400 megahertz and a 600 megahertz, and we can run spectra like this. So you take this molecule to us, we bring it to us, we can give you a spectrum like this and tell you what that particular molecule is, just based on something like this that you could probably do. So at this stage, at second year, in your career, you can actually take simple molecules like this and work out a structure, right? My master's and PhD students, we do complex molecules, 20, 30 carbons long, and 20, 30 carbons in a ring. Basically, we work on heterocyclic molecules, but it's much more complex than this. But at second year level, you can do something like this. So let's look at this particular molecule. And because we know what the molecule is, so we start off by cheating a bit. I know what the molecule is and looking at the spectrum. And you can see that this A protons here is different from the 2 outer protons, CH2s. So I've got 3 CH2s in this molecule. The first CH2 is different. This middle CH2 is different from the other 2. And can you see my center of symmetry that I have here? And because I have a center of symmetry down here, what you can see is that I have 1 B here, and that's also a B, right? So both these CH2 groups are equivalent, and that's 4 protons, and this CH2 group in the center is by itself, right? Now let's determine the multiplicity here. So I'm not seeing the other part because this is symmetrical. So this CH2 group is next to a CH2 group, right? So B is next to A CH2 is next to a CH2, and this is going to be a triplet. So B is going to be a triplet. A is also next to a CH2 group on one side and a CH2 group on another side. But remember, we're not seeing the other part of the molecule, right? We're only seeing this as a CH2 because these 2 groups are equivalent, right? So what we're seeing is 1, 2, 3, 4 protons, right? 4 protons that are adjacent to this protonated group here. So if I apply the n+1 rule to the 4 protons, and I think I did this with you in the other lecture, right? So the n+1 rule applied to 4 equivalent protons is 5, which is a quintet. Right, so I should get one triplet, right, which is the B signal, and a quintet, which is the A signal. And if I look at here, you see I can't really see what's going on in the spectrum, so they've been nice and they've expanded it for us. Right, I can't really see what's going on here, so they've expanded it for us. And can you see that this peak here expanded is the triplet? And this peak expanded is the 1, 2, 3, 4, 5 lines, and this is the quintet. All right, that's a quintet, not a quartet, because there's 5 lines here and 3 lines here, so that's the triplet. All right, so you can see very easily that this is my this is my B proton, and this is my A proton. Right, so the B proton is a triplet because it's next to the CH2, and the A proton is a quintet because it's next to 1, 2, 3, 4 equivalent protons. Right, so a simple spectrum with 2 peaks, a triplet and a quintet. All right, slightly a little bit more peaks, and let's see what happens in this particular case. All right, so I've got slightly more peaks here, and if you can't see things clear, I'll just show you, I'll tell you what they are. So if I look at around 5 here, right, I look at 5, I see there's a whole lot of peaks here. I can't see very clearly what they are. But if I look at the expansion, so they've expanded the 5 part out here, right? And if I count the peaks here, I get, there's a small one on this side and a small one on that side. 1, 2, 3, 4, 5, 6, 7, right? So that's 7 peaks, and that's a septet, right? 7 peaks, and that's a septet, and that's this resonance that we find here, right? They've also expanded this resonance here, right? It looks like a singlet here, but when they've expanded it, they saw that this is a doublet, right? So this is a doublet that we're seeing here, right? So between 1.8, they've expanded this and they've put it here so you can see clearly what that is. This here is just a multiplet. I can't see anything here. This I can see clearly on my side, it's a triplet, right? There's 3 lines, and I can see also clearly this is a triplet on my side, right? In the exam or so, I'll make it such that you see very clear spectra, so nothing is ambiguous. All right, so I've got a triplet, a doublet, a multiplet, a triplet here, and then this is a septet. All right, so I'm going to go to my structure. As I said, I'm going to cheat a bit and look at the structure and see if we can assign each of these peaks here. Now, there's many things that you can do to assign peaks. And you've learned about chemical shift, you've learned about integration, and you've learned about splitting pattern. And you can use one or more, or one and the other, to determine which peak is on which particular resonance, where the peak is in this particular spectrum, right? I'm going to look at the most de-shielded one first, this 5-1 here. And I always like to start with being most de-shielded. And if I look at the most de-shielded one, I look at the proton that's 2 bonds away from the oxygen atom. And that's your E proton, right? So the E proton is the most de-shielded in this whole group, in the whole molecule. So this must be my E proton. Now let's try and verify that by looking at the multiplicity, right? So I looked at the chemical shift, and the chemical shift said this should be E. If I look at the integration, I just have 1 proton here, and this 1 proton tells me the integration also matches what I said. Now let's look at the multiplicity. I see 7 peaks here, septet. And if I look at the environment here, this CH group is next to 2 equivalent CH3 groups, right? You can go home and you can actually see whether the CH3 groups are equivalent. You'll find out when you draw your stick structures that this CH3 and this CH3 is equivalent. That's why they called it BNB. And if I apply the n+1 rule, I get 6 plus 1 is 7, and the 7 peaks give me a septet, right? So I can say I'm happy with my E. I can then look at the other de-shielded peak. So the next de-shielded peak is here, right? At 2.2 or so. And as I said, if something's around 2.2, it probably is next to or 3 bonds away from the oxygen, and something can be 3 bonds away from the oxygen if it's next to a carbonyl group, right? So this CH2 group that you find here for D, I suspect this might be D. Let's see if I'm right. I look at the integration matches 2 and 2. And then I look at the splitting pattern. The CH2 group is next to another CH2 group, which makes it to be a triplet, right? 2 plus 1 is 3. And this is a triplet. So I can be confident in the fact that that is D. I'll then go to the rest of the terminal methyl group. I'll go straight to the terminal methyl group A because I know it's next to a CH2 group. So that must also be a triplet. And I look for the other triplet, it's here. So this must be A. All right, and you can see this A is integrated to 3 protons, so that's fine. All right, I've got 2 more resonances. This middle one, as I said, is a multiplet because I've got a proton group here and a proton group here. So this multiplet C, I can see integrating to 2 protons. This got 2 protons on it, so that must be fine. And then my equivalent CH3 groups next to a CH group, so it must be a doublet, and I see a doublet here. And that CH3 groups can integrate to 6, like we're seeing it here, right? So this must be my B. All right, so a slightly larger molecule, but you can actually assign all the peaks in that molecule using NMR spectroscopy. All right. The next example that I want to show you involves an aromatic ring. All right, so if I look at this particular spectrum, I have 3 resonances here, but I actually have more than 3 resonances because there's some overlapping resonances in this region, right? And if I look at this spectrum, we've been dealing between 0 and 4, generally up until now. But as I told you, between 5 and 6, you get double bond protons, and between 6.5 to about 8, you get aromatic ring protons. So this is the first example that you're seeing now where you have aromatic ring protons. And can you see here, I've got 1, 2, 3, 4, 5 aromatic ring protons, right? These 2 are equivalent because of symmetry. These 2 are equivalent because of symmetry, and then this E1 here. So, right, so I've got 5 protons here in the aromatic region, all right? So this is the aromatic region where you've got 5 protons, all right? So generally when the signals overlap, I can't really distinguish between E, D, and C, right? So these are due to C, D, and E. I can't really distinguish them because they're all overlapping in this region. And then I have 2 other groups. B, must be a quartet because it's next to something with CH3 groups. And there's my quartet here. It's telling me something around 2.5 is the quartet, right? So this must be my B signal. You can see it integrates to 2 protons as well. This A signal, right, is next to the CH2 group, so it must be a triplet. I can see a triplet here, right? You might not be able to see it, but trust me, this is a triplet, 1, 2, 3 peaks, and this will be due to the A signal. All right. Now, I also want you to take notes that the CH2 group, when it's next to this ring, now remember that the ring protons were de-shielded because of diamagnetic anisotropy, right? And I discussed what diamagnetic anisotropy is. You can look at the previous videos and you can actually get that, right? So if you've got protons in that vicinity, right, it's not directly affected by diamagnetic anisotropy, but it's close to that. So can you see how your CH2 is slightly more de-shielded than the CH3 because your CH2 is closer to the ring. So if you've got a proton group that's directly bonded to an aromatic ring, it behaves as such that, like a carbonyl group as such. So it de-shields the signal to around 2 to 3, right? And that's why you see the signal a bit more de-shielded here. Right, so this is an example of where we get aromatic ring protons in our molecule. So I'm going to show you one. So I said here we can't distinguish between these aromatic ring protons. let me show you one where we can distinguish between the aromatic protons. Right, so I've got this particular molecule here, simple molecule nitrobenzene. And this nitrobenzene molecule that you see, let's make it slightly bigger for you. Right, you can see if I apply symmetry again, these two protons are equivalent, those two protons are equivalent, and that proton's equivalent. So I'm going to see three resonances, one for A, one for B, and one for C. Right? Now I'm not going to discuss ortho, meta, and paracoupling with you this year. Right? You'll probably do that when you get to third year honors, but you know, I'm not going to discuss it with you this year. It might just confuse you slightly. So for your purposes, we're just going to use splitting patterns here. Now, if I look at C, C is next to one proton, this A proton here. So if C is next to this A proton, I'm going to expect a doublet, right? And if I expect a doublet for C, you can see that I have a doublet here, right? So that doublet is C. They're telling us it's a doublet because they expanded it out here. So this is a doublet, and that's my C, right? If I look at B, right, B's got one proton, and this part is one proton. They've expanded it here. And you can see this B is next to these two equivalent A protons. So this B must be a triplet integrating to one, and that's what you find here. Right? Now, unfortunately, you also find a triplet here for these two protons, that we have for A. Right? So the remaining resonance we have is A. Right? So this is the expanded version of A. Right, so that's B, that's the expanded version of C, right? And if I look at the expanded version of A, right, it looks like a triplet, but it's not exactly a triplet because C and B are not equivalent. They only become a triplet if they are exactly equivalent. So although it appears as a triplet, it only appears like that because the resonances are very close together and they overlap, right? So technically A is not a triplet, right? So this is not a triplet, although it appears like that, right? Because B and C are different, right? But B is a triplet and C is definitely a doublet. Right, when you get to higher years, you'll see that we have ortho, meta, and paracoupling. So if we run it on a very sensitive NMR spectrometer, we can pick up double doublets and triplets of doublets and quartets of triplets, etc., etc. But we're not going to do that at your level at second year. All right, so these are the spectra that we're going to see, and I'm going to end off the lecture by discussing one example where I'm not going to give you the structure, right? So I'm not going to give you the structure, and we're going to see how to tackle this, and then we'll pick up in the next lecture. We'll have a little bit more of these types of molecules where you don't have the structure, you just have a molecular formula and you have a spectrum, and you're asked to now get the structure here. So I'm going to show you one for today, and we'll pick up with this next week. So here I have a molecular formula of C9H12, right? So very importantly, 9 carbons and 12 protons in this particular spectrum. And if I look at this particular spectrum initially, I can see I have peaks in this aromatic ring, right? Integrating to 5. So if I have peaks in the aromatic ring integrating to 5, immediately I can put down an aromatic ring. Right? And this aromatic ring has got something on there, right? I don't know what this is yet. And it has 5 protons, 1, 2, 3, 4, 5 protons, right? I'll put the protons in for you. 5 different protons. I've got something else bonded there. We'll see what that might be in a second, all right? And I've only got this resonance for the aromatic ring, then I've got 1, 2, 3 other resonances. If I look at my integration, I've got 2 protons, 2 protons, 3 protons, all right? I remember that I have 12 protons in an entire molecule. If 5 are taken up by the aromatic ring, I have another 7 here, and that gives me my 12. So it's more likely to be a CH2 group, a CH2 group, and a CH3 group, right? So it's most likely to be those groups. Now let's see how we can actually put those together, right? In order to put that together, I would need to know something about the splitting pattern. And you can see that they've taken this resonance out, they've put it here. You can see that this resonance is a triplet. This resonance is a multiplet around 1.8, right? So I wouldn't go counting the resonances here, 1, 2, 3, 4, 5, 6, anything like that, right? Because there might be some overlap. So this is a multiplet. And then this I can see as a triplet. They've expanded it here. So that's another triplet. All right, so I must join these 3 groups up such that one is a triplet, the other one is a triplet, and the other one is a multiplet. And if I put the 3 groups in, all joined to each other, can you see the CH3 group is now a triplet? This CH2 group on that side is a triplet, and the CH2 group in the center will be a multiplet. So I have 2 fragments. Something must be joined there. I have 2 fragments. I've got this propyl fragment that I have here, which matches the multiplicity here, right? And I've got this aromatic ring, which matches the chemical shift of this particular resonance. And I need to join these 2 together. I don't have anything else. I've got 9 carbons, and I've used up my 9 carbons, 6 carbons here and 3 carbons here. So all I have to do is join the 2 together. And if I join the 2 together, I get the structure that's equivalent to this spectrum. And very quickly, can you note that this triplet, which is a CH2, is de-shielded because it's next to the aromatic ring, right? So I know now that this CH2 is this one here because it's next to the aromatic ring. The next CH2 in the middle, because of the multiplet, must be this one. And this one, which is most shielded, is next to, or is in this region of 1. And then these 5 protons here are here. Right, so just a taste of what's to come in the next 2 lectures that I will have with you this week. But that's how you can actually take a spectrum and get the structure of the spectrum just by looking at the structure, the NMR spectrum and the molecular formula. So thanks, guys. It was a good lecture. I'm going to stop recording, and I'm going to